So let's contrast that with the type 2 regions, which we're looking at this way. So in this case, notice that my y limits of integration are just some number. There's no curve here. It's just some number. And so, that might be because the intersection of the two curves where we're thinking about x as a function of y, the intersections are at a point like they are in these two examples, or maybe we just are given those limits of integration here. But these are all called type 2 regions. Okay? And again, the whole point is that even a more complex region, can be broken down into a bunch of either type 1 or type 2 regions. And so we'll learn how to do that in class, but for right now, we're going to say, hey, it's either going to be a standalone type 1 region or a standalone type 2 region. And I do want to be a little bit careful, folks. It turns out you can actually think of, you can take a general region, like maybe the first one we saw, where we had, maybe a triangle like that. And you may want to think of that as either a type 1 region going like this, or you may want to think of it, let's redraw that region, or you may want to think of it as a type 2 region going like this. So this isn't a hard and fast, it's either type 1 or type 2 in some cases, especially these more geometric ones. But every region can be broken down to either a type 1 or type 2, in some cases like this one, or both. But anyway, once we've got a type 2 region, how are we going to integrate it? Well, in this case, the choice is the order of integration, right? So we've got the double integral over our region R of f of x, y. How are we going to integrate this, dA? How are we going to integrate this? Well, if you draw these cross-sectional slices that we have here, here's the first you imagine some function living above here like we did in that previous image. Okay, those cross-sectional slices are going to start at y equals d, and they're going to, actually y equals c, because we're going to start down below here, and then they're going to stop at y equals d. So we want the outer integral to be from y equals c to y equals d, which makes our inner integral, so the outer integrals are going to be a function with respect to, or integrated with respect to y, so the inner integral is going to be from x equals, and then the lower curve, which is given by these images, g of x, up to x equals the upper curve, which is given by f of x. So there's that upper curve there, there's that lower curve there, of whatever this function is, f of x, y. Let me do all this, and I should keep that monochromatic. So that's our, I'm using the letters f here. I'm not. This is a g, and the upper curve is h. Good. Folks, I just miscopied. I thought this was an f here. It's an h. That's good, because then I'm going to use, for our function that lives above this region, our multivariate function is f of xy dx. Okay, so that's how we go about integrating one of these type 2 regions. Okay? This rewriting of the double integrals as iterated integrals is simply an extension of Fubini's theorem. However, unlike the previous version, because notice that this has a function here and this is a constant, I cannot simply interchange the limits. Now, there are some cases where you may be able to integrate it either way, but it will involve using some inverse functions. So in general, you can't think of just simply rearranging the order of integration with these problems. Okay, so now let's go ahead and look at this region R. So here's our region R here, and we want to find the volume of some function, f of x, y, or the net volume of some function that lives above this region. So the question is how are we going to write this as an iterated integral? Okay. Now, you could, if you wanted to, set this up and think of it as a type 1 region. Notice I drew these vertical lines there. Vertical lines go with the type 1 region. But notice how complex this is. We've got, at some point, we'd have to change what our lower curve is, and we'd have some interesting issue with our upper curve and lower curve being the same curve. This might seem a little bit reminiscent of what you did in Calc 2 when you were doing volumes of revolution. Anyway, I want to go ahead and set this up as a type 2 integral. Okay, so we're thinking about this as a type 2 region. So we're setting it up so we're going to do the iterated integral this way. We're going to integrate this from y equals negative 4 all the way up to y equals 5. Careful, that's the, this is the semicircle with a radius of 5. So those are the coordinates 0, 5. So our y values range from -4 to 5. Again, you think of these cross-sectional areas, and we're adding up a bunch of cross-sectional areas, starting with y equals -3, or excuse me, y equals -4, all the way up to y equals 5. And then what's our inner integral going to be? Well, that's going to be the integral from x equals, and then what is our leftmost curve here? Again, when you drew these horizontal bars, you're saying from this endpoint to this endpoint. Well, the left endpoint is the curve x equals, we got to be a little bit careful here. This doesn't look like x equals, so we better rearrange it. If I were to solve this for x, I'd get that x equals y minus 5 all over -3. So we get that x equals -1/3 y plus 5/3, all the way up to the upper limit. That's this curve up here, right? So as I drew those horizontal bars, we go from the left curve, from the left endpoint to the right endpoint. On the right side, we hit this semicircle, so that goes all the way up to where x is equal to the square root of 25 minus y squared of whatever our function is, f of x, y, and we're going to integrate that with respect to x. Again, I want you to think about this. This is one cross-section for a fixed y value. And then we're going to go ahead and then add up all of those different cross-sections from the y values -4 to the y value 5. And that's what that integral would establish for us. Okay, folks, this has been a long pre-work. I've got a couple more problems for you to work. The first thing I want you to do is simply sketch the region and then determine whether it's best evaluated as a type 1 or a type 2. So again, after you've sketched the region, you're going to either draw, like we did up here, you're going to draw horizontal bars. And if that's the case, you're going to consider it a type 2 region. Or like up here, maybe you'll draw vertical bars. And if that's the case, you're going to consider it as a type 1 region. Okay? So folks, go ahead and evaluate these two regions, or go ahead and sketch these two regions and then decide whether they're best integrated as type 1 or type 2. You can check your answers here. And then I want you to actually practice evaluating some integrals over generalized regions. And if you need any help, we've got solutions for you there to take a look at. That's all I've got for you, and let me know if you have any questions.